Hello, today we're gonna talk about rational maps and dominant maps, and we'll mainly follow Vakir's note, and we'll do an exercise which is also from the notes. So let's start with the definition of a rational map. So a rational map pi from a scheme X to a scheme Y, which we denote by pi from X to Y, and you'll see in a minute why we'll write the arrow like this. So this is an equivalence class of morphisms, namely, we have so it's a morphism from a dense open subset U, or a dense open subset of X with the following equivalence relation. Namely, we have, say, alpha from U to Y, and we have beta from V to Y, and they are equivalent if and only if there exists a, let's call it C, subset of X, or of course of X, but also of the intersection of U and V, which is dense open, such that alpha restricted to C is equal to beta restricted to C. Okay, that's the definition. Let me give a short remark, namely, in the situation where X is irreducible, all open subsets are dense, or all non-empty open subsets, so that's not really a restriction. Okay, and now let's give the definition of a dominant rational map. So a rational map pi from X to Y is called dominant if for some representative, so we have this equivalence class, and we have a representative from a dense open subset U and this map to Y, if the image of this map is dense in Y. Okay, and you can check that this is independent of the representative, so that's important. And so that's what dominant means. And what we are gonna show now is that we have the following lemma. So a rational map pi from x to y of irreducible schemes. Schemes is dominant if and only if it takes the generic point. So it takes the generic point of x to the generic point of y. Okay, so let's prove it. So let's take psi to be the generic point of x, and eta to be the generic point of y. Okay, and now let's start with the direction we have that it takes generic point of x to the generic point of y. So we have that for all u in x open, we have that the generic point is in u. So we get that the generic point of y is in pi of u. So that's by assumption. And what we get now, so this let me say, so we have that psi is in all open sets, so therefore we can take, maybe let me call it v. So if pi is defined on v, then we get that psi is also in v, and then we get that eta is in pi of v, and therefore we get that y is equal to the closure of eta, because it's the generic point, and then it's also the closure of pi of v is y, so we get that pi of v is dense. So let me write it here. So pi goes from v to y. Okay, that's the first direction, so let's prove the converse. Namely, now we use that pi is continuous. So what do we get? Well, let's see. So we look at pi of the generic point, and we look at the closure, and here we look at the closure in v, sorry. So the closure in v, and this is pi of v. So that would actually need proof, because we know that the closure in x is x, and it's also true that then the closure of v and the closure in v is v. But we don't justify this here, but so let's go on. So now we use continuity, namely here we use continuity. So by continuity we have this subset relation. So we have pi of psi and then the closure. So this is by continuity. And now we take the closure, taking the closure, so in Y, and using that pi is dominant, we get the following. We get that Y is equal to pi of V closure, which is a subset of pi of this. So just if we take the closure here, then we get this. So we get that Y is equal to the closure of pi of xi. So we can also write this as pi of xi, this map, and the closure of this point. And we have a unique generic point in the scheme Y. So we get that pi of xi is equal to eta. And that proves the converse direction. Okay, so that's what I wanted to cover in this video. So if you want to see, or maybe let me give you one more example. It's also in the notes by Vakir, namely an example of a rational map. So that we know that the notion actually makes sense, but so dominant maps are actually, so they can be important for birational equivalence. But so if we have this projective n space and we want to define a map to projective n-1 space, so where A is just some ring, and we define it like this, so just taking the n minus first coordinates, then clearly this isn't defined on the whole projective space, but it gives us a rational map. Okay, so that's it. Yeah, that's it. And so thanks for watching, have a good day, and bye.